Background and literature. This case study examines the structural failure of traffic light poles in Johannesburg CBD and Braamfontein, where a complete collapse rendered them non-functional. The primary causes of failure were identified as vehicle collisions, visible external corrosion, internal rusting due to trapped moisture, and stress propagation from microcracks originating during steel manufacturing. The poles made from hollow tubular graded steel suffered from internal and external corrosion. Externally from mud retaining moisture at the base, and internally from water seeping through the welded seams and joints with no drainage path. These factors caused progressive loss of wall thickness and structural strength. The final failure was triggered by a low-speed vehicle impact, which, combined with sustained wind-induced cyclic loading, generated bending stress that the already weakened structure could no longer withstand. In this case, the traffic light pole in Figure 1 failed due to a combination of mechanical and material factors. A minor collision introduced bending stress, one of the most critical stresses in structural members. The pole was already weakened by corrosion at the base, and over time, repeated wind loading caused fatigue damage, even below the material's yield strength. Pre-existing microcracks from manufacturing act as stress concentrators, allowing the cracks to grow and eventually join, resulting in brittle fracture. The root cause of failure was the combined effect of corrosion, crack propagation, and cyclic stress, which led to the sudden collapse from a moderate impact.
Proposed redesign of traffic light. There are some design elements to be considered. Firstly, material composition of the traffic light pole. Current status quo, hot dip galvanized S355 graded steel is used due to its properties of strength, durability, and resistance to corrosion. However, graded steel has a low ductility which can cause cracking upon impact. It is proposed that galvanized mild steel be used instead, as it has a significantly higher ductility due to its low carbon content. This means that shock can be absorbed and kinetic energy released through plastic deformation, heat, and vibration. Therefore, the process of a collision is slowed down, reducing the impact force, increasing safety. This leads to a deformed shape rather than complete breakage, so traffic lights can still be partially operational after small collisions. Mild steel is also low cost in comparison to traditional graded steel. Further, both steel types have similar corrosion resistance levels and will be galvanized to increase corrosion resistance. Comparison of them can be seen below. Two elevated bays. The traffic light will be elevated with a concrete pedestal to act as an impact buffer, which becomes the primary contact surface in case of a collision. This also limits corrosion by preventing moisture in mud or water from collecting near the base and damaging protective coatings seeping into the light structure. However, the base should taper as it increases in height so that vehicles do not make direct contact with it. Breakaway bases are implemented to reduce the damage caused during severe collisions by introducing controlled failure through the incorporation of intentional weak points. This aids in the absorption of shock. This feature should be included in the proposed design using chromium at the base of the pole as well as notches in the material to direct crack propagation. This limits damage done to the rest of the pole structure for easy repair.
Polypropylene foam. The proposed design introduces the insertion of the polymer EPP into the hollow interior of the traffic light to act as a protective barrier. The EPP foam has a significant recovery ability to its original shape after when the load has been applied to it. When the traffic light pole becomes into contact with the vehicles during collision, the gases in the polymer EPP will compress and allow for large deformation of the material without changing the stress to absorb external energies. Wiring housing. The wires in the buried tubes between the main control box and the traffic light should be long enough so that if the traffic light fails, they do not break. This will ensure that the lights can still work after when the pole has been involved in a collision. Okay. Pole geometry. To improve both the structural performance and corrosion resistance, the geometry of the proposed traffic pole should have a tapered profile and a fully sealed base. The tapered profile will enhance its structural performance. It will improve stiffness by optimizing material distribution along the pole's height. It will also help reduce the wind-induced vibration and minimize the stress concentration at the base. A fully sealed base will be designed by the welded end caps. It will have the drainage hole slightly above the ground level, and it will also be protected with the stainless steel mesh covers to block the debris and prevent the clogging. Engineering drawing of proposed design. On figure 8A, we have the CAD drawing of the proposed design, and on 8B, we have exploded version of the proposed design.
Manufacturing and processing techniques. The concrete base is taped with greater slope with a vertical height of approximately 0.5 meters. This prevents direct contact of the vehicle with the pole during a collision. The tapered sides minimize the damage of the pole by absorbing some of the kinetic energy from the vehicle to increase the contact time during the collision. For the breakaway base, the chromium metal undergoes a low temperature rolling process, after which weak points are intentionally made using fiber lasers. Rolling increases the brittle nature of the metal and the weak points are used to direct the fall of the traffic pole. For the EPP foam, small virgin EPP beads are placed into a furnace, melted and molded into a hollow cylindrical shape to fit the pole housing. These beads are utilized due to its exceptional ability to absorb energy. For the pole housing, the raw materials are melted in a blast furnace to produce molten pig iron. Oxygen is then blown through the iron to reduce the carbon content present, thus forming mild steel. The steel is later immersed in molten zinc to finally produce galvanized mild steel. The elimination of carbon is to increase the ductility of the metal to prevent shattering. The assembly starts with securing the chromium metal to the concrete base. The EPP film is bonded inside the pole using adhesives, which is then positioned over the hollow chromium section. The base is then welded to prevent water seepage into the pole. The light signal head is mounted last with all the minor components properly integrated. The images below display the main materials used in the proposed traffic light design.
Physical evaluation. From Table 1, key difference is that the new design is of galvanized mild steel with a chromium section and an elevated concrete base. It also uses EPP foam inside the pole and there's a small drainage hole. On the other hand, the current design is of graded steel with a 10-year life expectancy. The polycarbonate housing is the same across both designs, and for deeper comparison, mild steel is more ductile than graded steel. In the new design, the elevated concrete slab minimizes crash impact, the small drainage hole allows for water exit, and EPP acts as a crash shock absorber, all which are absent in the current design. The key component in the new design is the breakaway section, which ensures that crash impact does not affect the upper part of the traffic pole. Additionally, drivers are much safer as the pole does not offer resistance to knock over in case of an accident. The predicted mode of failure is from fatigue cracking on the traffic pole and the light housing, and the expected lifespan is from 20 to 25 years. Potential weakness is that the chromium breakaway section is vulnerable to cyclic loading, meaning failure can happen anytime, inevitably. Additionally, impact of the drainage or on the structural lifespan has been overlooked in this research. For future recommendations and future projects, the main material can be changed to duplex stainless steel, which offers superior corrosion resistance, a very high strength and ductility. The use of finite element analysis to optimize thickness and predict failure points can be incorporated, and strain gauges can be used to measure bending stress and fatigue. These will be connected to a low-power Internet of Things module that transmits real-time data to a municipality dashboard for predictive maintenance using machine learning. The images below show the microstructure of duplex stainless steel, mild steel, and an example of finite element analysis used on a pole.